Information Technology at Arkansas State University in Jonesboro, Arkansas. He holds a BS and MS in Mathematics and MS in Operations Research and Statistics from Rensselaer Polytechnic Institute in Troy, New York, and a PhD in Operations Research from the University of Massachusetts at Amherst. He has served on the faculty at Texas Tech University, the University of Louisville, University of New Hampshire, University of Massachusetts Lowell, and West Virginia University. He has numerous publications in journals. His research interests include data mining, text mining, web mining, database management and mathematical modeling, and supercomputing applications. His research has been funded by the U.S. Air Force, U.S. National Aeronautics and Space Administration, Arkansas Biosciences Institute, and Arkansas Science and Technology Authority. He is a member of the editorial board of the International Journal of Data Mining, Modeling, and Management, the International Journal of Data Sciences, the Open Cybernetics and Systemics Journal, and the Open Medical Informatics Journal. He is co-editor of a book titled Visual Analytics of Interactive Technologies, Applications to Data, Text, and Web Mining, published in 2011 by IGI Global, and is nearing completion of an edited book titled Research and Applications in Global Supercomputing, to be published by IGI Global in 2015. Thank you very much.
Okay, thank you. The title of my talk is Research and Applications in Global Supercomputing and Interdisciplinary Study. And Thomas, you talking about DNA databases. I'll talk about that in applications of supercomputing shortly. Okay. How do I get the next? How do I?
Right arrow.
Right arrow. Did someone come up and?
To your right.
Look in the arrow pad
Yes.
down there.
Click.
You hit the right arrow.
Arrows on your right-hand side.
Oh.
You're talking about supercomputing.
There we go. All right, thank you. All right. Supercomputing is a computer at the forefront of current processing capability and speeds of calculations. They were first introduced in the 1960s, but they only had few processors. And in the 1990s, they had thousands of processors. In the 20th century, we had 10,000. And in the 21st century, we had 100,000. Whoops. There we go. Sequoia is a third-generation blue gene computer from IBM, which runs on 1.6 million processor cores. It can reach speeds of up to 20 petaflops, and petaflop equals 10 to the 15th operations per second, which means that Sequoia can perform 20 times 10 to the 15th operations every second. However, it does require 3,000 gallons of water per minute to cool it down. It uses 6 or 7 megawatts on the average, with peak usage approaching 9.5 megawatts. And that runs to about $6 or $7 million a year just in power alone. Here we have one of the first supercomputers in 1963, which I said had about 1,000 processors. This was at the University of Manchester in England. Here we have a Cray computer in 1985, which had about 10,000 processors, and it has the shape of a C, which was their trademark for the supercomputers. Here's one in 2012 at Argonne National Labs, the Blue Gene supercomputer. And here's one at Lawrence Livermore Labs, the Sequoia computer. Okay, here we have a timeline up to the year 2019. And you see that in 2003, we had the human genome mapped. And in 2005, we had the Millennium Run simulation. And in 2008, the petaflop barrier was broken. But in 2019, they estimate that the exaflop barrier to be reached. Okay, here we have performance of the first 50 supercomputers. And as I said, that the first supercomputers had up to 1,000 processors, and up to the 1990s, we had up to the 10,000s. And in the 21st century, we went beyond 100,000. So since that time, we've actually have actual supercomputers that the top 50 computers that actually go to almost 10 million processors. Okay, the top supercomputer in the world as of June 2014 is in China, and they beat us out last year. The U.S. is no longer is the leader. Is no longer the country that has the fastest supercomputer. China took us out at their National University Defense Technology, and has a performance of 33.86 petaflops. And this, every 6 months, there's a top 500 list that's recalculated or recomputed of the top 500 supercomputers in the world. And they were announced at the 2013 International Supercomputing Conference in Leipzig, Germany. It's called the Tahani 2 or Milky Way 2 supercomputer, which is in China. And it came out 2 years ahead of the expectation. And it has 16,000 nodes, Intel Xeon Ivy Bridge processors for a total of 3,120,000 computing cores. Okay, the Human Brain Project uses supercomputers, and this is a funded project which has about 200 researchers in many different countries, and it's the largest, most ambitious cooperative experiment of its kind. It's budgeted to be $1.6 billion, and it packs a simulation into a single computer to require a system 100,000 times more powerful than today's supercomputers. In other words, they're mapping the neurons of the human brain in the supercomputer project. Okay, here's a list of the top 10 supercomputers as of November 2013. Number 1 is in China, as I said, the National Supercomputer Center in Zhangzhou. The second one is in the Department of Energy at Oak Ridge National Labs in the United States, and that's a Titan Cray XX7. The third one is at the Department of Energy at Lawrence Livermore National Labs. That's a Sequoia, which I just showed you. Number 4 is in Japan. It's the Riken Advanced Institute of Computational Science. Number 5 is at Argonne National Labs at the United States. Number 6 is in Switzerland, the Swiss National Supercomputing Center, which is a Cray XC30. Number 7 is at the Texas Advanced Computing Center at the University of Texas at Austin, and they have a Stampede Power Edge, which is by Dell. Number 8 is in Germany, and that's a Blue Gene. Number 9 is in the United States at Lawrence Livermore National Labs again, and that's the Vulcan Blue Gene Q, Power BB, etc. And number 10 is in Germany, and it is a Dataplex, Xeon, etc. And there's statistics on each of those. Okay, so the second fastest supercomputer in the world is in the United States, which is at Oak Ridge National Labs. It previously was number 1, but was taken over by China about a year ago. And that has 17.59 petaflops on the line pack benchmark using 261,000 accelerated cores. And it's one of the most energy efficient systems on the list, consuming a total of 8.21 megawatts and delivering 1.43 megaflops per watt. Okay, here I have some pictures here of distribution of the supercomputers in the world. And table 1, which is on the next slide, lists each of the countries in the world that have at least one supercomputer and ranks them according to their system as far as the share of the top 500. And I also have some other statistics there, R max and R peak. It shows the frequency curve for the, figure 2 is a frequency curve of the number of supercomputers for each of the countries presented in table 1, and statistics shows the locations of the world's 500 most supercomputers in the world. And you'll see from that, those two tables, that of November 2013, 264 of the world's leading supercomputers are located in the United States. Okay, so here we have my table here, and you see that the United States has more supercomputers than anybody in the world. We have 264 of them, which is 52.8% of the share. China has 63. They have 200 less, and they have 12.6%. Japan is 28, or 5.6%. United Kingdom is 23, or 4.6%. France is 22, or 4.4%. Germany is 20, or 4%. India has 12, or 2.4, and Canada has 10, or 2%. And all the other ones are just, they just have a handful. In fact, Russia only has 5 of them. Only has 5 supercomputers, which is 1% of the system share in the world. Okay, so here I plotted those numbers to show, and so the United States is way above everybody else as far as number of supercomputers. China is only 63, and the other ones, as I cited the numbers there, and the other ones are, minimal. Whoops, I'll go back here. Okay, here I have a video which shows some of the multidiscipline applications of supercomputing.
Hi, I'm Matt Meade, Governor of Wyoming. I want to welcome you to the Enterprise Wyoming Supercomputing Center. We are very pleased to have this supercomputer here in Wyoming. I'm here with my friend, former Governor Friedenthal, Governor Friedenthal. Governor Reagan. My name's Dave Friedenthal, and I was governor from 2003 to 2011. The development of this project was a partnership that came together with great energy and enthusiasm both from the state of Wyoming and from the federal government. This facility is important because it will add to our knowledge about the interaction of storms, weather, drought, wildfires, energy production, agriculture, and all of those things are important in the West, but they're also important in the United States and throughout the world.
What is the atmosphere? The atmosphere is a very thin layer that surrounds the entire Earth. It's about 6 miles thick. And it contains everything: oxygen, nitrogen, the air we breathe, and almost all of the weather. Clouds, thunderstorms, tornadoes, hailstorms, hurricanes, blizzards, and rainbows. The atmosphere also carries pollen, smog, air pollution, and the greenhouse gases that cause global warming. Sometimes the atmosphere literally comes down on our head, whether it's low-lying clouds or a fog-like mist. The atmosphere is dynamic, it's beautiful, and it's constantly changing. Our discipline cannot survive without supercomputers. They do things like simulate the climate, help us predict where severe weather will occur, what storms will produce tornadoes, floods, help us figure out where air pollution will be transported, and really start looking at things that affect people's daily lives, if not for their future generations. We try very hard to make our science relevant to the general public.
Original supercomputers were room-sized and really didn't have any more capability than today's cell phone. Weather models weren't very accurate. A severe storm looked like nothing more than maybe a small blob on a screen. Today we're much better with the accuracy, but greater accuracy requires more computing power. More computing power requires more processors. This facility has been designed to handle that demand into the future. A computer is nothing more than a bunch of circuits. When a circuit changes its state, converts from a 0 to a 1, it gives off heat. For this facility, we use tens of thousands of processors. Computers malfunction when they overheat, so it's critical that we keep them cool. We've taken advantage of the region's climate. This building brings in cold air, exhausts the hot air, and we also recycle the heat throughout the rest of the building. This facility was designed to be energy efficient and flexible. Some of the key energy efficiency features are floor vents, this large fan wall, and we also take advantage of renewable energy such as wind.
This is actually very technologically complex. There's 72,000 individual processors located on over 4,000 nodes, and then these nodes are all interconnected via a high-speed interconnect fabric that lets them communicate with each other. So it actually makes it one computer. Cable management, as you can see behind me, is a huge challenge here. There's over 12,000 cables. Every cable is labeled, it's tested. So despite the angel hair pasta look, there's a lot of order in the disorder. One of the biggest challenges when you have all of these processors trying to talk with each other is moving data between them. So there's really two things we worry about. One is latency and the other is bandwidth. Moving data around is a lot like plumbing. Latency is the amount of time you wait for that hot water to get from your hot water heater to your sink. Basically the time from point A to point B. Bandwidth is like the gallons per hour you can move through the pipe. So it's the volume of data that you can move. At any given time on this computer, we're able to move billions of bytes of data through tens of miles of cable on this system. And moving that data is just critical to actually doing the science.
Imagine millions and millions of grid boxes spread out over the Earth in a mesh in 3 dimensions, stretching from the bottom of the ocean to the top of the atmosphere and into outer space. And these grid boxes are where the physical quantities are stored. For example, temperature, pressure, and wind velocities, and they're calculated upon using the laws of physics in chemistry and thermodynamics. And each processor takes a relatively equal chunk of these boxes and works on that part of the problem. So in the same way that ants in an ant colony might work together to accomplish something, these processors all team up and use the network to work on the same task. However, the way the laws of physics work, you need to actually talk to your neighbors to find out what's going on next to you to do these calculations. And that's where the communication
study important issues related to climate, to weather, the atmosphere around us, to energy, to water and ecosystems, to how all of these systems interact with the human system. What we as humans do greatly affects the world systems, and supercomputers allow us to model these Earth systems and take into account complexities and interdependencies that we've never been able to before. Supercomputers are one tool. It augments experimental theory, but because of the complexity of these problems, supercomputers are in many ways the most efficient and the most powerful tools at this particular time. At the University of Wyoming, we are already integrating the use of supercomputers into our classes, both at the undergraduate and the graduate level. We find that supercomputing allows our students to have a real interdisciplinary experience and provide them with skills they'll need for their future careers.
One example for how supercomputers help us better understand the Earth system is by modeling the sea ice and looking at its influences on the atmosphere and on the ocean, we can get a good sense of how variations or long-term changes in the Arctic sea ice pack are going to affect the atmospheric conditions, precipitation, rainfall, snowfall, and the general climate. Sea ice is incredibly important for the Earth's climate. It acts kind of as the Earth's refrigerator. Sea ice is a very bright reflective surface. What that means is that it reflects a lot of sunlight away from the Earth's surface and causes the Earth's surface to cool. So when you replace ice with open ocean, you lead to a situation where you absorb a lot more heat. And that gets you in this vicious cycle where you absorb more heat, you melt more ice, you absorb more heat, and so it just acts to amplify warming in the system. Our models solve the equations that describe how sea ice moves, how it melts and grows in response to winds and ocean currents, and how it regulates the transport of heat from the ocean into the atmosphere. So the sea ice component of our climate models describes all of these different aspects. And that piece interacts with an atmospheric model, an ocean model, a land surface model, and all of those parts of the climate system interact, exchange heat, exchange water, precipitation. We have equations that describe all of these things. What this requires is a vast amount of computational power, which means that we have to use supercomputers to study this problem. Supercomputing gives us the capability to look at the Earth using a virtual laboratory. Supercomputers allow us to study the interconnectedness and the intricacies of coastlines, urban areas, habitat, animals, and the food web and biodiversity. Supercomputers are allowing us to look at all these different aspects of the problem, how all these things are interconnected, how they impact and modify each other. A better understanding of climate science is critically important for people because we have to live in this climate. So we need to understand those variations, those changes, those interconnections, because it affects us.
Okay, I have another video here. Whoops. There we go. This is the National Center for Supercomputing Applications.
My name is Evan Burness, and I work for the private sector program at NCSA. We are a different group than most at NCSA, whereas most of the folks who work here focus on open science missions, which is part of our mandate from the National Science Foundation. An extension of that mandate is for helping companies compete better through advanced modeling and simulation. When you make something by hand, which in our world we call experimentally, you're always limiting the amount of good data that you can collect about how high the quality is of the product you are trying to craft. When you do it with a computer, though, you can explore the design space in far, far greater ways than you can in the real world. I'll give you an example. Let's say you are Rolls-Royce and you make aircraft engines, and you wanted to test out 500 different variations of the same engine design. In the real world,
Okay, this one's about 2 minutes, I think. I get my...
It's a massive machine in a massive room. And what it's working on could change the way we make scientific discoveries for decades. The recently launched Titan supercomputer will tackle the world's biggest problems.
Titan uses about 9 megawatts of power. That's as much as a small town of about 4,000 or 5,000 people. It also uses about the same amount of water as a town of 4,000 or 5,000 people to cool it.
Enough to power a small city, and it took a small city's worth of manpower to put it together. Housed and operated in the Oak Ridge National Laboratory in Tennessee, part of the U.S. Department of Energy, rocketing straight to the top of the world's most powerful computers list with NVIDIA GPUs inside, like the chip in your PlayStation 3, but designed for science.
The kinds of problems that get solved in both of those instances, either in scientific computing or in gaming, they actually have a lot in common.
We take advantage of that. These GPUs do the same type of calculations to create those pictures on the screen that we need to be able to do to make pictures of what's going on in the universe.
We build processors that go into mobile devices all the way up to supercomputers, and there's a tremendous amount of design leverage across and up and down that spectrum.
Now, to get a sense of just how powerful Titan is, consider that it can calculate in 1 hour what your computer would take 20 years to finish, and they're just getting started.
About every 10 years, computers have been getting 1,000 times faster than they were before. And we've been doing this for several decades now. When we reach the first petaflop, that's a million billion operations every second.
And that kind of power doesn't come cheap. It costs $9 million a year just for Titan's electricity bill. But thanks in part to the GPUs inside, Titan is actually 5 times more efficient than the previous model. And what it gives us is a glimpse into what happens next.
Think of a supercomputer as a time machine. The simulations that we do on the machine today are trying to predict what's going to happen in the future. And so with a more powerful computer, we can look farther into the future to try and understand what's going to happen.
Okay, I actually skip this one. This one is also 2 minutes.
University of Chicago researchers say they used 1/4 of the Beagle's operating capacity in conjunction with commercially available software packages to analyze raw sequencing data. The time and cost of sequencing entire human genomes has dropped dramatically in the 21st century. Unfortunately, it can take months to analyze the results, given that there are 3.2 billion base pairs to decode. As such, it's become popular instead to focus on fewer than 2% of the genome that codes for proteins, in a process called exome sequencing. Now researchers out of the University of Chicago are reporting in the journal Bioinformatics that one of the world's fastest supercomputers devoted to life sciences can analyze 244 genomes in 50 hours. They estimate that the same task would have taken a single 2.1 gigahertz CPU more than 47 years. To be clear, tapping the extraordinary powers of the Beagle, named after the ship that carried when 22-year-old Charles Darwin on his scientific voyage around the world in 1831, isn't going to keep the cost of whole genome analysis down, which is of course an imperative if the tech is to be clinically useful. It does, however, demonstrate that genome analysis has the potential to be far, far faster than it is today. The supercomputer can process many genomes simultaneously rather than one at a time. First author Milan Pakelwat, a postdoctoral fellow at the University of Chicago, said in the school news release, it converts whole genome sequencing, which is primarily being used as a research tool, into something that is immediately valuable for patient care.
Okay, I have some graphs here to show the comparisons of the countries around the world. The first one is on teraplop per country, and as this next figure shows, the United States is the leader with China, Japan, Germany, and France lagging behind. U.S. is way ahead. We have 118,261 teraflops. China has 48,549. Japan 22,472, etc. And if we take the logarithm of that, it shows it in a different scale.
Is this capacity or what they do on the average daily? I mean, what is
It's their capacity for their capacity, because they don't use 100% of it all the time, every day. I'm just saying this is just.
Do you have charts on what's actually used?
I don't know if I have utilization rates on those.
Because one of my questions is, all your slides are speaking about how costly this is in terms of heating electricity.
Right.
I assume it's cost effective. What are you saving in money? I mean, and you're spending all this money on these computers. What are you saving in exchange for it?
Well, as one of the time. I mean, like it said like it took like 2 years to do something they could do in in a couple of seconds or
But
something.
how much is that problem worth? You solve the problem in 1 second, you can do it in 2 years. But how much money does that problem generate? Does it compensate for all the money you spend?
Right. If you have clients that are paying you to analyze big databases, you get more clients in the same interval of time.
There's some things that we don't know how to put value on. The medical breakthroughs that you see with the human genome, right? You don't see
Right.
values of neural being able to predict. I mean, in the Olympics 2000, we were able to predict within a block or two where it was going to rain and the weathers and so on. So,
Right.
the value of being able to make those kind of predictions.
But aside from which, as I was saying, look at the four-color theorem proof. Now, granted, that wasn't a huge supercomputer, but not much numerical value, business value. But there's also a value in knowledge. You can't just...
I wasn't asking my question in a doubting sense, but when you have this much money being spent on one resource, namely computers, and there are competing resources, you often wonder, in terms of dollars, what is being saved. And if I had a pie chart, part of the pie chart could be problems like Olympics and other things. But what's being saved that has monetary value or
Well, supercomputers have higher dimensionalities of data capabilities of analyzing. So you can analyze, like I'm going to talk about supercomputings for DNA. Thomas talked about this earlier. I have some slides here to talk about that. Okay, here we have megaflops and took the logarithm of the country, the top 500 supercomputers. This is per capita, so that means income of the residents. Okay, and Switzerland is way up on the top there, above the United States, and that's the logarithm of that. Okay, here I have some pictures of the number of people per supercomputer per country, and I have two graphs here. We have a line graph and a bar graph. The United States is the leader in number of supercomputers, but it's the lowest in the number of people per supercomputer. Okay, so India has a big population, so obviously the number of supercomputers per person is different. Is above. United States is all the way down here because India's population is in billion. Yeah. Okay, here we have a count of the 274 supercomputers per continent, and Western Europe counts for 85% of it. North America has 274, 54.8, Eastern Asia 99, 19.8, etc. Here we have, I broke up the architecture cluster or parallel processing. Cluster has 84.6%, 15.4% of it MPP. Here we have tables of operating systems for the top 500 supercomputers, and the most is AIX. Here we have processor generation, the top 500 supercomputers in the world, and Intel Xeon has 61.4% of it. Here we have operating systems for the top 500, and Linux is 96.4% of it, Unix is 2.2%, and the others are much lower. Applications, most of them are unspecified. 82% were not specified for any particular area. As I said, this is multidisciplinary, so I mean, weather and climate, energy, defense, benchmarking, they're minimal, but most of them weren't specified. Again, a lot of these things are used for unclassified information also, so we don't know. India, these are the list of the top supercomputers in India, and the highest one is rank 44, and that's the India Institute of Tropical Meteorology. Here we have comparison of supercomputers between different countries. India had only 12 or 2.4%. China is 4.6. And these are not ranked numerically here, but United Kingdom is 4.6, the United States 52.8. Here we have the operating systems. Linux had a system share of 96.4%. I just put these in bar graphs, what I had in the tables. This shows the aggregated distribution to the top 500 industry of most of them, which was 56.4%, followed by research and academic. And as of November 13, infinite band was the interconnect family used in 41.4% of leading supercomputers. It's this one here. Here I have a bar graph of the number of supercomputer cores of the 10 fastest supercomputers in the world. And Germany has Eugene from IBM as the maximum. IBM had a share of 32.8% of the top 500 supercomputers worldwide. That's in this bar graph right here. Stenography, the art of concealing a message within a message, is a type of encoding whose operations are required to remain secret, not only on the algorithmic level, but also on stenographic function that's performed that should be kept secret as well. Okay, supercomputers have been used for this, and Dan Offer, who's also presented at WMSCI in the past, did some research which he contributed to my book, talking about data mining methodologies for this. And here we have two figures here, and you see the resolution is obviously different. So he's using algorithms within algorithms in data mining, and he's superimposing the images, but he's doing this by supercomputing. Here we have different tracks in the sequence of nucleotides of the p53 gene. Supercomputing has been used for. With also programming paradigms in high-performance computing. Here's a graph of electronic energy consumption as determined by supercomputers. Logic is also a language of supercomputers, and I have two slides here by Jeremy Horn, who's right here, who can comment on these if you need be. Supercomputing language uses zeros and ones, and it becomes the multitude of these becomes even more intensified with supercomputers. And he also has a three-dimensional hypercube showing about the logic that's used in supercomputing. And again, with the number of cores that we have, this is actually magnified and intensified. Education for supercomputing leadership. I mean, now that we have supercomputers, people have to learn how to, what a supercomputer is and so forth. So here I have a graph of different types of areas here. Supercomputers have also been used in the defense area. And this is for anti-cancer drug. And here we have one on applications of pattern recognition and gene modeling. Someone just asked me, I've done a lot of work on applications of supercomputers, and I just have a couple of pictures here that shown of things I've done in other previous publications of that supercomputers have been used for, visualization using supercomputing for design purposes and so forth, microarray databases. I did supercomputing analysis at the genomic level for lung cancer. These are all done by supercomputers. Here we have a volcano plot of lung cancer data. One-way analysis by condition or patient. These are heat maps and dendrograms which show the intensity of the data for breast cancer, training set data, petition tree data for breast cancer, and so forth. And this is the end of my talk here, and I hope I've been able to give you an overview of the interdisciplinary applications of supercomputing and their usefulness and so forth. And it's really a new era in research.